Hi everyone, I'm Weitao, a second-year PhD student from RISE, working with Professor Eugene, and today I will introduce SpiderMon, a data plan diagnostic system. This is a joint work with Dr. Praveen Tammana from Princeton and also Professor Chen from RISE. The performance degradation problem is sometimes hard to debug in today's data center network. Take the following network for example. This is a part of a factory network. Consider we have a green latency sensitive flow sending from server 0 to server 7 through the green path. And there is a small control flow from server 1 to server 2. This red flow is acceptable because it won't create extra latency for the green flow. But there is another latency insensitive flow without rate limiting, start from server 3 and head to server 4. This flow will generate contention at switch 0 with a green flow. And there is another brown flow who also contend with the green flow at switch 4 because it was sent to the wrong path. If we take the yellow path, it will not contend with the green flow. In this case, the green flow is a victim flow who experiences high latency due to multiple contentions along its path. But the problem is hard to debug because root causes is located at different places across the whole network. I concluded three reasons for the difficulties of debugging. The first reason is that the latency problem happens sporadically in the network, meaning the problem may happen on any flow with any path at any time. The second reason is that one specific problem may involve multiple switches across the whole network. And the last reason is that the problem may last only for a short time and die away very quickly. If we want to catch the root causes for those transient problems, the debugging system needs to retrieve the information very quickly. And there are many performance-oriented diagnostic systems, and we can group them into three different kinds. The first one is always-on system. Those systems collect information all the time from all the nodes, and use those information later on for debugging, which will introduce high storage overhead and make the system hard to scale. Another kind of solution detects the problems on the switches and relying on the control plane to retrieve the information across the network and do the debugging. Those systems maintain a low storage overhead, but the control loop latency is high because they need to send the information to the control plane and let the control plane make the decision. After that, the relevant information stored on the switch may already be expired. The last group is even more problem-specific. The query-based solution generates queries to collect network information and rely on the predefined queries to cover all the nodes that are related to this problem. So this kind of solutions can only debug predefined problems. They cannot cover all the problems in the network. While our system SpiderMon debugs the problems in a reactive manner. At the very beginning, all the switches will only execute the monitoring task, which will monitor the accumulated latency for every flow, and also maintain the causality information and the telemetry information in the switch data plane. Until one of the problems are found on one of the switches, that switch will generate the audio request and start the broadcast procedure, and also trigger the debugging tasks on itself and on other switches. Note that both detecting problems and receiving an audio request from other switches will let the switch start executing the debugging task. For the debugging task, switch need to do two things. The first one is to multicast the audio request to other nodes that was related to the problems. The second task is to report the telemetry information to the diagnose agent for further analysis. After executing all those two tasks, the switch will back to the monitoring mode and wait for the next event. This slide shows the problem was found on switch 4, meaning that the accumulated latency exceeds the threshold on switch 4. And SpiderMon were trying to find out all the relative nodes in the network. And in this picture, we show that all the relative nodes that are relative to the problems on switch 4 was found out by the broadcast of the audio request. So the problem comes to how we guide the broadcast with the provenance model. We choose to use the provenance model to find out relations. For a specific latency problem, many events may contribute to the problem generation, like contention along the historical path and also the wrong routing decision of other flows. But maintaining an accurate provenance graph is difficult in the switch data plane. So with this limitation of the switch data plane, we choose to maintain an approximate provenance graph with two strategies. We can see that the cumulative latency is introduced on switch 0 and switch 4, and exceeds the threshold on switch 4. So switch 4 will start the debugging task first. The first strategy is to trace back the victim flow, because the accumulated latency may be introduced at the previous hops. So the audio request will be sent back with the historical path. In this picture was switch 0, 1, and 5. Besides that, the second strategy is to trace back the contention branches, because all the contention branches that contain with the victim flow is also included in the provenance graph. So we will also trace back the contention branches with the audio request. As you can see in the picture, it's switch 7 and also switch 2 and switch 6. Once all the relevant switches has received the audio request in the network, they will report the telemetry information to a diagnose agent. And this diagnose agent will be able to identify potential root causes of the problem by analyzing the telemetry information stored in the switch data plane. In this case, the diagnose agent has identified the potential root causes to be switch 6 and 7, and also server 3 and 5. And there are more details about the data structures in the paper, and you can take a look at the paper. For the experiment, we show that with typical data center environment, we can achieve less than 1% false positive rate with less than 1 megabytes memory size for each pipeline in the switch. And there is a trade-off between the precision and the overhead. We can always get more accurate result with larger memory footprint. Then we come to a conclusion. We present SpiderMon, a data plane-based system that diagnoses performance problems accurately with low overhead. And we also implemented a prototype for SpiderMon with BMV2 model. We validate that SpiderMon can achieve high accuracy with low memory consumption and also low bandwidth occupation. And this is all for my presentation, and thank you all for listening. Thank you.